pleasure for us to welcome Yin-Jie Ma from East China University of Science and Technology. It was a really pleasure to meet you and actually to learn about your work with your colleagues and with the colleague whom you know. So it's really interesting also how you try to map together two fields of simplicial complexes reconstruction and evolutionary games. So really looking forward.
Okay, so shall we start right now? Okay. So my title for today's discussion is Reconstructing Simplicial Complexes from Evolutionary Games, because I am a PhD student in East China University of Science and Technology, and my major research interest is located in evolutionary games. And this work is finished and furnished during my stay with Professor Stefano Boccalti in Italy, and with my supervisor Zhiqiang Jiang's guide, we are going to incorporate these two fields to rebuild or infer the topological structure of a high-order network in evolutionary games. And I'm very pleased to be invited here and present my work. It's also my honor to see that one of my colleagues, Fan Shu, is also invited here. So the intuition of our work is that we have seen a lot of complex networks in real life. But the main problem is that sometimes we can know their structure. Maybe in friendwork matchup, you can learn a lot about their friendship between strangers or something you know very well. But sometimes it's not possible to infer all the friendship or the network links, especially the high order or hyperlinks from the surveys or something like that. But it's essential to know the structure before we got something to do with this network. For example, if we are going to learn something from the mechanics that can result in the emergence of cooperation in complex networks, sometimes we assume that there is a Barabasi-Albert network, or there is a known network to build. And based on these networks, we have some gossips or something like the information diffusion to learn these dynamics on a specific network structure. But in real-world data, we can always find some flaws for this assumption, because if we collect information, we always concentrate on some personal information like the yearly income, and it's also very hard to infer all the topological structures in a network, especially in high-order networks. So to solve this problem, first we have already have some planned methods to infer the structures in the the simple networks where there are only links or edges. So for example, we have comparative sensing to incorporate the adjacency matrix and the strategies they have in a simple network. And we also have some Bayesian estimation to infer the largest likelihood that there is a friendship between two specific friends or strangers. And we also have some machine learning methods to infer the potential friendship or the network link. But these methods, sometimes they have some, they cannot infer the high order networks because they have some multiple solutions to this network, so that we have to find another way to define how we do this or solve the same question in a high order network. So for this paper or for this work, we focus on a way that we only know the personal information like payoff information or the strategy information from evolutionary games. And we can reconstruct the higher order networks displayed by the simplicial complexes with this payoff or strategy information. The first step is that we have to define what we have in our hand. So we assume that we already know the dynamics of different people. They follow some evolutionary games.
Just one question. You also see, you change the slides, right?
Yeah.
No, I don't see the changes of the slide.
Okay. Maybe I have to reshare my screen, right? Let me see. Is it okay right now? So you can see my switching of the slides.
I see the. Yeah, Misha.
Yes, I can see it.
Okay.
Okay. So we first assume that there are two kinds of games built respectively one simplicial and two simplicial. So for one simplicial, it's traditional games like pairwise games, and it is qualified by the T and S, these two parameters. And if we disentangle these two parameters into two levels, they can be divided into 4 different games. And S is the cooperating, the payoffs that a cooperator can receive from a pairwise game, and the T is the opposite. The other is that if we consider a higher order game that involves more than 2 players, let's say 3 players, they are playing a 3-body games in a 2 simplex. So there will be 8 outcomes according to the different combinations of different players' strategies. So if there are 2 defectors and 1 cooperator, then the defector will get the payoff T and the cooperator will get G. If there are 2 cooperators and only 1 defector, and then the defector will get the payoff of W and the cooperator gets S. So these are the basic procedures that we have for to get the information about the strategies and the payoffs of different players. So we can aggregate these payoffs if we know the structure. So let's say A1 is the adjacency matrix of the 1 simplicial, and A2 is the adjacency tensor of the 2 simplicials. And if there is a 2 simplicial between player I and J, then A1 IJ will be 1. So it's simple to see that our equation here can be defined for how we calculate the specific payoff that a player I can get at the time Tm. And the Pij1Tm is kind of the single payoff that player I can get from his interaction between with the player J. And then we can record this payoff information and strategy information to build them into 2 matrices. Let's say there is a large pie, and it contains all players' payoff information in all the time. And let's say Tm is the time to differentiate all the payoffs that they get in different time. And S is the strategy information matrix. Because we have to infer if we don't know the structure, we have to infer the structure topological characters. So we have to define the potential payoffs in 1 simplicial and 2 simplicials. that's based on the strategy information. If we have the strategy of I and the strategy of, let's say, player one, so we can calculate the pay one. We can calculate this one. So this is only calculated by these two strategies, and we can iterate, we can enumerate all the outcomes according to the different strategies. Then we put them together. We flatten all the adjacency elements in the matrix and the two simplex adjacency elements in the tensor. And these are the main targets that we want to infer because they can represent what we want to know about the higher order networks presented by one simplicis and two simplicis. And we also define all the potential payoffs and adjacency matrix into a matrix and the tensor. Yeah. So our problem is that if we know all the potential payoffs and we know all the potential strategies, how we infer this AI, which is the flatten of all the adjacency elements, including all the elements that represent one simplicis and two simplicis. Can we infer this matrix? Yeah. So here we propose three methods to infer this AI. The first method is called point-by-point estimator. We call it point-by-point estimator because we infer the adjacency elements related to a single player, let's say player I. We only infer this player's adjacency elements one by one. So we can see that if our target has been changed to minimize this this matrix one norm, and we also include a two-form penalty to avoid that if there is a noise in the measurements of the pi I. But this solution is usually quite sensitive to the noise because we in real world when we do surveys and we collect information, sometimes we have some measurement errors or some noise distortion. So we have to use this two norm penalty to increase our accuracy. And then because this is not after we use this method to infer AI, the elements in AI is not binary. It ranges from 0 to 1. So we have to filter some elements that is close to 0, so that there is a little chance that there will be a two simplex or one simplex in this network. So we did use this threshold parameter to filter the real one simplicis and two simplicis. We first sort all elements in the one simplicis and two simplicis. That is called these two guys. And we calculate every gap between elements. So we can find there is a large gap. And we define this largest gap as our threshold method, our threshold parameter to filter the real simplicis. So let's say there is pi delta I1 for one simplicis. It's maybe 0.05. So any AI1 larger than 0.05 will be capped, and they will be defined for one to indicate there is a one simplex between two players. Also, we can calculate delta I2 for each player that every element in the two simplicial adjacency tensor that is larger than delta I2 will be kept. So we can drop any two simplex ijk, or if any edge ij, ik, or ijk is missing from the network. So we can so this filter method keeps us guarantees us to filter some to drop some two simplices or one simplex that is less likely to appear in the real network topological structure. But this method has a flaw that we can see that if we concentrate on the player i's adjacency, this is estimated by player I, and this is estimated by player j. So there can be inconsistency between these separate estimation, because aij1 is estimated by player i's adjacency matrices. So it can be estimated by 1. And this could be estimated by 0. But in real world, we always assume that it's symmetric, because if player I is a friend of player j, so player j is also a friend of player I. So they have to be symmetric. And this constraint is also extended if we estimate the two simplicist elements, because these elements has to be equivalent, but these two elements are estimated from player i's adjacency matrices, and these are estimated by player j, and these two are estimated by player k. So these inconsistencies will always appear in the methods that we have mentioned in, let's say, PVP estimator. So we have to overcome this flaw, and we propose the second method that is called global estimator, because in this method we incorporate all the adjacency elements into one row or one column. So you can see that there will be no overlapping elements or the lower scripts. We can see that there are no identical lower script numbers in this column. So we only estimate aij once. There will be no inconsistency in this method. And of course, we also do the same thing for the elements in the two simplices, and we define it as A#2. Again, we put this or concate them together to put them into integrated A#. So this A# is now our target to infer, and every element has to be 1 or 0, so that we can see there is a two simplex or one simplex existent in the result that we have gained. So this is the payoff matrix that the potential payoff that we get for this method. And again, we put them together. So now our target is to infer this A# in this form, and we drop the lower script for I, because we only we estimate every element in A# once, and we also use the threshold method to filter that some inconsistency between the one simplices and two simplices. And these simplices are removed to be 0, so that there will be no inconsistency in our reconstruction method. But there are also some problems in this global estimation, because a two simplex has to be built on 3 one simplices. So let's go back to this figure that these 3 are pairwise games. Pairwise games and this triangle is 2 simplex, and it has to be built on 3 1 simplices. That means that if we have a group of 3 members, and these members has to be each other's friend as well. So this is also a constraint that we have to consider to make a perfect reconstruction in our simplicial complexes. So the global estimator with simplicial constraints is our third method to propose here. And the biggest difference between block method and the globe method is that we incorporate these simplicial constraints here, because we have to maintain that 1 simplexes has to be existent to form a 2 simplex. And these are the 3 methods we propose in our paper. And then we have to use these methods to infer the synthetic high-order networks and the real networks. For synthetic networks, we use Killian-Kovalenko's method, and we build some synthetic simplicial complexes. So the first model is non-preferential attachment model, and during this method, each link is chosen randomly, so there will be no preferential attachment in this method. And then we use also preferential attachment model to construct the synthetic complexes. And we also use mixed model to mix these 2 methods together and systematically to finish the synthetic complex build for our problem. So we assume that there is already known network structure, and we gain the strategy and the payoff information with this structure, and we reconstruct this structure to verify that our methods are effective or robust to some noise distortion. So this is for the synthetic complexes. And we also use some empirical complexes because some researchers or reviewers has raised some comments that because we are only built on the synthetic data and they are too far away from the real world data. So we collect some high order networks in real world data, and they are called Malawi village, because this is a face-to-face contact data set conducted in Malawi village. And we also have 2 additional real world data to test our methods. So here are the results for our reconstruction methods. And the left column here is the method for the reconstruction results for the 1 simplices. It's pairwise games. So we can see that if we compare the F1 score here, our 3 methods are almost exactly the same, especially in these 2 games, in these 2 type of the synthetic networks. So we can get a nearly perfect reconstruction effect. But if we go to the 2 simplices, then we can find PVP may be not a good method to reconstruct the the high order interactions between the 3 players. So we can see that there is only 7% 0.07 F1 score for the method that we use for PVP to reconstruct the 2 simplices. So these are the same for the results that I mentioned before. So we conduct all these reconstruction methods according to different kinds of games, and Glow and Glock can always reach relatively higher or accuracy, and especially Glow can reach a perfect, almost perfect reconstruction when we only consider one simplicial and two simplicials in the syntactic complex. There's another problem that in real world, because if we have to do the reconstruction in a real world data, we have to do the surveys and track their daily life or the daily information they have. So there's a problem that if we can use these methods to reduce the samples that we have to collect for the perfect reconstruction. And we can see that the PVP can never reach a relatively high or perfect reconstruction, because it's the highest accuracy or F1 score for PVP method is nearly 0.8, and it has to it has to be built on a relatively larger data set, because we can see that M is the sample size, and we vertically compare these methods that PVP needs more samples, and Glow and Glock can do a perfect reconstruction based on a relatively small data set in the syntactic complexes. And then we also consider the noise distortion in real life, because when we collect the data, we will meet the noise or the measurement errors. So we simulate these situations. We put some a random value called epsilon, and epsilon is meets the distribution of Gaussian. So Q will capture this the deviations of between the distribution, and the larger Q is the more noise there will be in our payoff matrix. And then we conduct the same methods on the reconstruction results. So we can see that Glock is always the best, even if there is a large, let's say 5% distortion on the payoff matrix. So we think it's already a good result, because 5% is a large distortion in real life. And we conducted these methods on all of our three syntactic complexes. It's always Glock that performs the best in all of the three methods. And again, if we consider the minimum necessary data set, that Glock is always the needs or requires the minimum sample set, because again, we vertically compare these results. So for Glow, it has to be built on 35 samples to reconstruct a high order network between 50 players. And if we consider Glow, it has only 25 samples to again infer the 50 players networks, the higher order networks in the syntactic situation. And because before we have mentioned the results in syntactic complexes, and again we tested our methods in empirical complexes in our real life data sets, and we can find that the results of perfect reconstruction are exactly the same, with Glow performs the best in all of our three methods. And it keeps the robustness with the noise and the minimum sample set here. Yeah, and compared with the empirical complex reconstruction results and the synthetic ones, we can find that we only need 15 samples here, because this is 15 samples here to reconstruct the, again, the n equals 50. So this is maybe because the sparsity of the empirical complexes. And if we consider this sparsity, block may perform better, and we need less data set to make a full or perfect reconstruction of the high order network. So the main idea of our paper or our work is that we have raised these three methods to do the fully reconstruct the simplicial complexes, and they have different applied situations. So for example, if you don't care about a perfect accuracy, and you only consider that there is a large data set for you to do the reconstruction, then PVP will be a fast and a rapid method for you to apply in the real world data. But for some smaller data sets, that is that you are really constrained by the costs to collect the real world data, then GLOW and GLOCK may be a good idea to consider, because they need more or less data sets to do the reconstruction. And they can perfectly reconstruct the high order networks at the same time. So according to the different usage and the different situations, these methods can be applied and to reconstruct the real world data, and to maybe in the future research, we will do some students, do some experiments on students, and we will invite them to do the experiments, because these are only conducted on the computer simulation, and we hope these methods will be also useful when we do it on the real world experience. Yeah. So that's the main idea and the main body of our the work. Yeah. Thank you.
Thank you so much. Thank you. Yeah, I wanted. Yes. Wait. Let me just make someone to join. Okay. Yeah. Maybe don't stop to share the screen, because it's actually great if you can share still, because we could discuss still and see some of the some of the slides, if you can go back to them, because so if I understand correctly, the estimator, the PBP estimator, the one which you are creating, the one which you are using, is indeed something that is not useful for when you are estimating or reconstructing the two simplex. The two simplices. And is there some specific reason for that? Like, do you have something that actually, because if I understand correctly, that is just you in PVP, you're just estimating the argmean of the maximum of the adjacency matrix, right?
Yes.
AI. So it's not something that you. Yeah, I'm just trying to find out whether there is any specific reason why some estimators would not work and some would work.
Yeah, because
maybe you could show it in your screen indeed.
So let's go back to the PVP results. So I mean, there is maybe the upper limit because all of the three masses only reach maybe around 0.8, right? So we think that because we have not incorporated too many constraints because two simplices are very sparse, and if we assume that there will be no two simplices, and it can sometimes increase our accuracy. So that's maybe a big problem because compared with one simplices, two simplices are more sparse. And we have encountered some problems that if we assume two simplices appear, we can get a better reconstruction.
Because it requires
that's
you.
Very weird.
Because it requires you the additional information, right? So you limit.
Yes.
Mm-hmm. Okay.
So that so that's why we put more constraints in glow and block.
Okay. But also I think that for those people who were or those people who left, but some people came. So basically, for me, this problem, if you go back to your formulas, just so that you kind of explain it a little bit. Yes, even actually in the formula, when you show the one simplex and two simplex idea that you're estimating, yes, so this one, right? So your basically the result of this estimation is that you want to estimate the structure. The reason why you optimize a threshold parameter is that you want the structure to be highlighted by this threshold, right?
Yes, because this is because when we estimate the elements of AI, there will be some tiny number of the elements, and although they are not zero, but we assume that there is a less likelihood that these two simplices or one simplices appear. So we have to find a optimized threshold to filter these tiny numbers. And then we use this method to do the filter. Yeah.
Because indeed, once you applied it, indeed you reconstructed, and also the results seem to be very robust. Quite high. So I don't see how. By the results, some of them. Because I was not familiar sometimes also how to read them, right? So M is number of observations, right?
Yes, yes.
Mm-hmm.
And F1 is kind of the accuracy because it's based on the true positive, false positives, the indicators. So the higher F1 is, the more accuracy our reconstruction method is. Yeah.
Okay. Yeah. Well, it's more or less. It becomes a bit more familiar. It's just very, very specific, oriented to this PVP estimator, which I think is also very specific. The literature maybe from which you took it also was quite.
Yes.
Specific, so I guess that the reason why you took it also is
because it's kind of a classification task because if we want to infer this method, essentially we have to define this value is 1 or 0, so it's kind of a classification task. And then we use this F1 score and ACC or AUPR, something very traditional, right?
Yeah. I don't think that it's good. I think that if you're using this, for some specific reasons, also, this. these measures. So yeah, and also the fact that you can recommend these estimators techniques for specific cases, right? When maybe in Malawi, I don't know actually this Malawi data set specifically, what's because you mentioned that indeed it has some high order edges, right?
Yes, because we assume that there is a higher order edge between or among different villagers if they have a contact lasting for maybe more than 10 minutes, I think. Yeah. So we assume there is a high order edge among these different villagers.
Yeah. Okay, so it's based on this. But so basically, you know the ground truth there.
Yeah.
In a way.
But the largest problem for this method is that in real life we don't know how they do the dynamic. We don't really know the dynamics, how they do the evolutionary games. That's a big problem. So and it's very hard to solve. Yeah.
Yeah. Yeah, I understand. Yeah, but for people who are working with the games in general, I think that it's generally a very difficult problem how to understand what are the to get some information. Also, I mean, in this case, you're using the contact data, right, to simulate some interactions.
Yes, so that's why we tried to do the experience, do the experience on the students to control the labs or something like that, to collect the real life evolutionary game data. Yeah.
Okay. Well, thanks a lot for your time and for coming so late, also for in your time zone. I think it would be it's really great to learn more from you about that.